Greetings. In my previous video, I solved the problem for you where there were humid air coming in from point 1 into an air conditioning system. It was humid but cold air. We did two things to it. First, we heated that air, and then we injected some water into it, and therefore we had warm, humid air out. And what we did, we calculated properties uh, from point 1. What we didn't know was specific humidity, where we calculated it. We also calculated all we needed for point 3. We didn't know specific humidity. We calculated it. If we didn't know relative humidity, we also calculated it. And this all gave me the opportunity to calculate mass conservation and also the energy conservation equations and calculate how much heat should be added to this problem, so that if we add this much heat, we would have point 3. But there is a problem to it once we come to point 2. What happens to point 2? And to see this problem much better, what we do is that I show this problem on the psychrometric chart. Now, the psychrometric chart gives us a very different picture, because if we have air coming in at this point, it's 5 degrees C and it's 50% humidity. And if we just heat it up, we would bring it to 30 degrees C, which is at this point. And this point is um, about 10% humidity, which is not good at all. If we inject water into this flow, it would follow the adiabatic saturation temperature line, which is this one, and it would give us the wet bulb temperature line. So inject water into this 30 degrees centigrade flow, and it would no way go to where we want. I mean, this is the final point that we are to reach, and it would no way go there. It will end up here. So you have to heat it up again, and then inject more water, heat it up again, inject more water. If you wish to heat it up and then inject water once, as you see, if this is the final point that you want to reach, then you have to heat it first to very, very high temperatures. I don't know, I don't have it on my psychrometric chart, but it has to be very, very warm. So, as it is, what we conclude from this point is that it can't be that we just heat the coils and then inject spray water into this at point 2. This doesn't just work. Now, the other alternative that we have to look at is when we have point 1, we have point 3, and we just mix heating and adding water. And as you see, that would follow the line, green line. And that doesn't work either, because right in the middle of the way, it goes somewhere out of the psychrometric chart, and it would be too much humid. In fact, what happens is that it doesn't go straight, but some water would be condensed, some condensation you would have. So at the same time, we are adding water and we are getting condensation. And in fact, somehow we have to do the same thing. I mean, it would be a more realistic way of achieving what we are achieving is a line like this, which won't happen. You see, a zigzag like this won't happen. So, practically speaking, it would be very difficult to just heat the flow and spray water into it. And there has to be some other solution to the problem. Now, let's look at it from a different point of view. Now, we had the problem that if we injected water into the stream, into air stream, then the water would act just like evaporative cooler and it would follow the adiabatic saturation line. But what happens if we inject steam into this flow? Not water, but if we at point 2, what happens if we inject steam and not water into the flow? Now, let's calculate and see if what happens if we first heat this water to saturated liquid level, say at 90 kilopascals, no problem, and then to inject steam into the stream after point 2. Now, what we need to do is to calculate how much heat do we require to turn this water into steam. And that is very easy to calculate. You see, all we need to do is to say that Q dot equals M dot, which is the mass flow rate of water, times what is the final condition we wish? It is Hg at 90 kilopascals. We have just boiled the water. That's all there is to it. Minus HF at whatever pressure that it was, which was perhaps the ambient temperature, but it is 10 degrees C. Now we have all the information that we need to calculate this value, and therefore Q dot would equal 0.0022 times 2670.3, and you see where I have taken that value from. It is just boiled water, steam, and that is minus minus HF at 10 degrees C, and that is 42.022. And the outcome for Q dot would be 5.782 kilowatts. And you see the value we had calculated for Q dot for this problem was 8.0549. So this is the total heat for our control volume between points 1 and 3. And the interesting point is that out of this heat, this much has to be used just to vaporize water. Now, let's just divide it. Of course, it will be a simplified look at it, but it will be a good look at it. See what happens if we use the rest of it to heat air, how much added temperature would air have, and then inject this steam into the air stream, air plus water stream, of course, but it was whatever that entered, to see what would the total act do. So what we do is that we just deduct these two values. We just deduct these two values, and therefore Q dot, which was added before we injected steam, added before point 2 equals 8.0549. 2.49 minus 5.782, and that equals 2.273 kilowatts. Now we have, this means that we have used this 2.273 kilowatts just to heat between points 1 and 2, and then injected steam. The steam we produced, and then brought our problem, our stream, to the final required condition. Now, if we do that between point 1 and 2, then a specific humidity won't change because there is no injection of water into the airstream. And therefore, if we want to repeat our first law equation, we will have just H in and H out, and moreover, W1 and W2 would be the same. So now between points 1 and 2, we may write the energy equation, and let's write it here between 1 and 2. The energy equation would be 0 equals H in minus H out, in at point 1, out at point 2, plus whatever heat that is needed. And expanding this for the air conditioning sort of problems, for the mixture of air and water vapor, that would be 0 equals m dot A times Cp0 Ta at point 1 plus W1 times HV1 minus m dot A times Cp0 Ta2 plus W2, and I'm writing all this between points 1 and 2, times HV2 and plus Q dot. Now, inserting values into it, 0 equals m dot A 0.1, 1.0045 times 278 plus W1, which is 0.00303 times HV1, which is 2510.1. That's all we need for the incoming stream, minus m dot A, once again, 0.1 times Cp0, 1.0045 times Ta2, which we don't know, plus W2, which hasn't changed from W1 because between 1 and 2 we have injected nothing, and that would be 0.00303 times HV2, which is a function of Ta2. I mean, if we know this temperature, we could know HV2. So these two won't be two different unknowns. And plus Q dot, which we know it to be, Q dot, we have just calculated it, and we know Q dot to be 2 points, which we know Q dot to be 2.273 kilowatts. Now, this is a trial and error type of problem, and for TA2, I have done my best and found that if I guess TA2 equals 300 Kelvin, then HG2 would be 2549.8 kilojoule per kilogram. Now, it's interesting because look at this value. This is 300 kelvins, and point 0.3 was 303 kelvin. So you see, the picture is very clear now. Out of 8 kilowatts, almost 8 kilowatts that we needed for heating this air, okay, we only needed 2.273 to bring this air 4.1 to 300 degrees at point 2. And then by injecting the steam into it, it is hot steam, its temperature is 96 degrees C, and that would just add the extra 3 degrees centigrade and bring our system to point 3. Let's look at it in the psychrometric chart. Now you see this is our new psychrometric chart. What we did, we just heated the incoming stream from point 1 to point 2, which is almost 27 degrees C. And then we injected steam, not liquid water, but steam. And the steam just was added to our original stream, and both increases humidity and also slightly increases temperature. And therefore, we ended up at our final position. So adding, you see, there were two alternatives here. One was to add air. One was to add our heat to air and then inject liquid water. See that liquid water would vaporize, where would it collect its energy for vaporization from the air. The second point was that to directly give temperature, give heat to the water, boil it, and then inject it into the coming stream. And we saw that this latter was a very possible case. It was very possible to reach the point you wanted, simple and straightforward. The former, where we had to heat the air and then inject liquid water into it, was basically impossible and very impractical. Thank you very much for watching, and cheers.